that is the area that you're interested in. So this will be your, so the distance from here to here will be your y bar. Okay. So now we're going to form the equation for the first moment of area. And for this case, you only need to consider the area for the webs. Okay, not like before that, you need to consider flange and the web. Okay, so you have Q y bar. Oh, sorry. First moment of area about a z-axis as a function of y. Okay. So the width. So again, you have twice left and right. You have 0.02 for the width. The depth is equal to 0.065 minus y, and then it is 0.065 plus y. Okay, and then you have to multiply by half. Okay, so this you have 0.02, then 0.065 squared, which is equal to 4.225. And then you have minus y squared. So this will be equal to 84.5 times 10 to the power minus 6 minus by 0.02 y squared. So if you look at this equation, it somehow look really, really familiar, right? So this is just considering the bottom. And then if we look at the previous one, this is our first moment of area, right? The values are the same. Okay, the values are the same as you can see. And these are all in meter cube, right? You got 84.5. Let me copy the equation over here. And let me come over here. And then I paste down here. You realize that this equation that we have, we derive from the bottom and the top are exactly the what? Exactly the same. Okay, so this is one way that you could check whether your answer is right or wrong. Okay, you take it from the at the centroid. This only work at the centroid. Okay, at the centroid, whether you take from the top or from the bottom with a constant thickness. Okay, if the thickness is constant, right, it will work from the bottom and at the top. Okay, if the thickness is not constant, it will not work anymore. Okay, so you realize that the first moment of area you got from the top and the bottom is the same. Then all I can do now is take the whole equation over here. All right, I can copy, and then I go down here. I can paste. Why? Because why I could do this is purely because only the first moment of area changes, right? And then the equation is exactly the same. Okay, so I just put this over here, right? The V is constant, the I are constant, the thickness are constant, and this value are exactly the same. Hold on, let me write this down. I've problem coupling, so it's equal to 32.707 times 10 to the power 6 minus 7.741 times 10 to the power 9 y squared. Okay. So what does this actually means? Okay. What does this mean? Okay. So now what we are going to do is we are going to sketch. Okay, I would like to sketch the shear stress distribution. Okay, we like to sketch the shear stress distribution. Okay, so Again, use this diagram over here. Okay. Then I'm going to sketch our centroid. Centroid. Then we're going to have our, I'm going to bring, oh, I'm lucky. Anyway, so this will be our axis. This is our Y. This will be our shear stress. Okay, this will be our shear stress. Then our shear stress will so up to here, right? This is, so I'll not put any numbers down. I just will sketch out the profile for you. Okay. So this is from here. So how this will look like is this, okay? So you have from 0, it will then have, it looks like this. And because the change in thickness occur, it will go up this way, right? And then from here, it will end up looking like this. Oh. And this function over here that you see, right? The function over here is equal to 32.707 times 10 to the power 6 minus by 7.741 times 10 to the power 9 y squared. Okay. And the other function over here, right, the smaller step, so-called step, is this function that we derived last week, which is equal to 9.483 times 10 to the power 6. So 9.483 times 10 to the power 6 minus by 7.741 times 10 to the power 9 y squared. And we know this is our tau max. And our tau max is equal to 32.707 times 10 to the power 6 Pascal. Okay, so this is how the distribution will look like. Okay, so I want you to have the confidence. Okay, if the thickness, like from here, right, we know that this is the centroid, right? If the thickness are the same below or on top of the centroid, right, deriving the distribution equation will be the same whether you take it from the top or you take it from the bottom. And you can see for yourself, it's so much easier to do it from the what? From the bottom, right? You can see for yourself, it's so much easier to do it from the bottom because the equation is so easy. It's just that function over there. Whereas if you consider the top, right, you can see the first moment of area, you have more components to consider. Okay, so either you take from the top or you take from the bottom. If the thickness is constant, your equation will be the same. Okay, and it is another way to check whether your answers are right or wrong. Okay, right. So the next thing I want, any question from anyone so far. Okay, if you feel that I'm going too fast, tell me. Okay, anything that you all need me to repeat. Okay, I don't hear anything. I would like to do yes. Someone put up your hand. You can ask me.
Sorry,
Yes.
I wanted to ask regarding from the top section, why did we subtract 20 from 35 in the QZ equation? I mean, 20 from 35. 20 over 2 from 35, rather.
So this one, right?
Yes,
Right.
yes.
So that is because it is the Y bar. Okay, what do I mean by Y bar? So we know if we view, I'm going to use a different color. So this is for the flange, right? So this is the Y bar now, right? So the distance from here to here is 20 divided by 2. Okay, and we
Ooh,
know that the overall distance from here to here is what?
35.
There you go.
All right,
Okay,
thank you. That makes
you're more
sense.
than welcome. Anyone else? Any question? I don't see anything on. Oh, I do apologize. I forgot to turn on the camera. Yeah, I do apologize. Okay, I'm going to do another interesting example. Okay, when I say interesting, interesting in a sense that it is not necessary that the centroid will always have the maximum shearing stress. Like for this example that I've shown you, right? It happened to be at the centroid where the shearing stress is maximum. Okay, and I'm also aware that when we derived last week, when we derived this equation over here, right? When we derive this equation over here, right? The maximum is also at the centroid. But it's not always the case. What do I mean by not always the case? For this case, you can see that the thickness is constant, right? For the case that we have, it happened to be the thickness at the centroid is the smallest. Okay, so I'm going to do one example for you that it's not necessary that the centroid has the highest shearing stress. Okay, so I've posted all these diagram on Avenue to Learn that you could see. Okay, so we are going to do this example now. So as I said, this is a very interesting example. Okay, so this is our example 2 or example 1. It was the one previously was a continuation. Okay, example 1. So let's look at the formula. So for beam having the cross section shown, determine the largest allowable vertical shear if the shearing stress is not to exceed 60 megapascal. Okay, so we're going to deal with this problem now. Okay, so what we have is the formula we're going to use, or what I'll do is I will copy the rules. Okay, that we have compiled last week. Okay, so I want to show you that we have to when applying all these rules, it's so much easy. Okay, so we know that the shear stress is equal to Vy. Okay, so I'll at the same time draw our transformation. So this is our y, and this is our z. Okay, we have Vy over Izz, right? Qz divided by t. Okay, you see that now. Okay, so the rule said that V and I are constant, right? So we know that, and we know that